Shridev has not joined yet. Chalo, theek hai. Let us start and then they can cover by the recording. Okay, chalo. So whenever we talk about heat transfer through extended surfaces, you see, let's say you have a body here. You have a body here where something is happening. Something is happening. Some Q is generated here or whatever. For example, your automobile engine. So fuel is burning, heat is generated. Okay. So this surface, the side of that engine or that body is needed to be maintained at a particular temperature. Let's say it is at this boundary x is equals to 0. Let's say here x is equals to 0, and you must maintain this as T naught, because this, let's say if it is an engine. Okay, so engine, it has some material restrictions. Okay, whatever material it is made of, cast iron or anything, it has some material restrictions. What do you mean by material restrictions? It can only sustain a temperature that is below a maximum temperature. Okay, if the temperature is above the maximum temperature, then there could be some deformation, there could be some setting changes inside the engine. Okay, and most importantly, if I am talking about IC engine, then what will happen? What is the phenomena that is very undesired if the temperature increases very high? For example, petrol engine, auto engine, what is the phenomena that is directly affected by temperature? Can anyone tell me for auto cycle, auto engines, SI engine, petrol engine? Anyone? If the temperature goes above a certain temperature, then detonation is the phenomena that degrades the performance of the engine. Okay, so you want that engine to operate. Are you able to, I mean, my audio and my screen is clear to you? Okay. So that is, there are so many reasons. There are, because, for example, a chemical reaction is happening inside the engine. So chemical reactions basically happens at a particular temperature. If the temperature is below that or higher that, it negatively affects the performance of that chemical reaction. Okay. So whatever products are formed, it will form some other product if the temperature is higher or lower. That is not useful for you. Okay. So basically you need to maintain a constant temperature, okay, inside the engine and at the boundary of the engine. How can you do that? By allowing the heat transfer to happen. Whatever heat is generated, you have that heat should be gone out, heat loss, so that you will maintain that body at a certain temperature T naught, let's say. Okay, this is what you want to maintain. So you can only allow this simple body, for example, this is your body, and let it allow the heat loss. Okay, so only area that is responsible for heat loss is this area. Okay, but now what we can do, we can increase, because we all know conduction heat transfer is proportional to thermal conductivity, area, and temperature gradient. Okay, so we can increase the conductivity, but this engine is basically made of certain material, so you cannot change the conductivity of the engine material. So what can you do? You can add an extended surface here like this. Now it is doing, now use this material of higher thermal conductivity. Okay, so now conductivity is increased, area is increased, and heat transfer through conduction will increase. So now the design of fins could be done in a way that it will be able to allow the heat transfer, the desired heat transfer. Ki bhai, I need to transfer this much heat so I can maintain my temperature T naught. Okay, is it clear? So that is why you use extended surfaces, not just one. You use many surfaces here. Okay, I have made just one. There will be a fin here as well. There will be a fin here as well. So many fins will be there. Is it clear now? So first of all, what will happen? There will be a conduction heat transfer. There will be a conduction heat transfer from this body. From what body? this body, okay, the engine body, there will be a conduction heat transfer inside the fin, okay. That conduction heat transfer will go like this. Now here, above this body, there is some air or some water. For example, if you have dipped your engine in water, so the fluid is water. Okay, but usually if we talk about our automobile engines, it is exposed to air. Okay, so air, because this body, this above surface and lower surface, you see this surface is also at a higher temperature than T environment. Okay, you see temperature is coming down as you are increasing your x direction. As you are increasing your x direction, here it is T naught, but when you go in the x direction, temperature will start reducing. Let's say T dash, whatever it is, but it is still higher than T environment. So there will be some heat transfer from the surface as well, which is Q dot convection from the solid body, from the solid fin to the surrounding fluid. Okay, is it clear? Okay, very nice. So what is the objective of using fins? To increase heat transfer rate. But what are your assumptions? Your assumptions are, first of all, steady state. Steady state means at a particular you need to maintain this temperature, not just this temperature. At any point the temperature will remain same itself. For example, here it is T1 dash, here it is T2 dash, T3 dash. So these temperature is decreasing as you are increasing x, but temperature at a particular location will remain same with respect to time. Then only you can be able to design. If these temperature will change, that means it will also change. Okay, so if you need to maintain T is equals to T naught at x is equals to 0, temperature everywhere in the fin will remain constant with respect to time, not with respect to x. With respect to x it is decreasing, I have shown you the graph, but with respect to position it is same. Is it clear? So that is meant by steady state. Now next is no heat generation. Heat generation inside the body is equals to 0. Inside the fin there is no heat generation. Heat generation can happen here, but not inside the fin. Okay, conductivity is constant, so whatever conductivity is there of this body, it will be constant. And H is also constant. Here this, let's say whatever air is here, it is as T infinity and H. So H is also constant and uniform throughout. Throughout means everywhere H is constant on the surface. It is not like this. If the heat transfer is taking place from this area, then H is different. And if it is happening at this area, then H is different. No, H will remain same throughout the surface. Okay, chalo. So fins are the projections made on the surface into the ambient to increase heat transfer rate. Where convective heat transfer coefficient is low, mainly atmospheric air is there, so it is low. I will tell you some other things about this. If you do not understand this, it simple means, for example, if you have this body, you see, if you have this body, and for example, and this is your engine, let's say this is your engine. If it is surrounded by, for example, water, so water heat transfer coefficient is already higher, much higher actually than air. So this fluid, this water can take away heat anyway. You do not need to use fins. But if this engine is working not in water but in air, then air heat transfer coefficient is much less. So heat accumulation will happen inside the body, and that is why you cannot allow heat accumulation inside the body. You need to allow that heat to go out. So you use fins. Okay, we will talk about this further as well when we talk about effectiveness. But if heat transfer coefficient is already high, then it's not effective to use fins, because fins do not increase heat transfer. Like basically, if you are increasing the surface area, you are using some material, you are using some manufacturing or machining processes as well. So there is a cost also included. Cost also comes when you increase the surface area. But if with this cost the heat transfer is not significantly improved, then there is no use of using fins. Okay, Already water is taking so much heat that by adding fins, even if you are increasing little bit of more heat, it will not change much. So it is not effective. Okay, let's move ahead. Chalo, very nice. Let's move ahead. Okay. So how do we do this and start analysis? So let us consider our straight rectangular fin producing producing मतलब going out, protruding from the surface. Okay, this is my fin. I can see this is my fin, and it is of, let's say this is x distance, and I have taken up any element inside this body with a thickness of dx. Okay, now what will happen? You see, some heat is conducted here. Some heat is conducted here inside the fin, and that heat will enter into this element q dot conduction x. Also, because this is out there, this area is out there, it is exposed to the surrounding, so there will be heat transfer, convective heat transfer from the solid body to the surrounding fluid, whatever the surrounding fluid is, air, water, whatever it is. And then from this fin, let's say this is q dot convection that is going out. So q in, and so q in is only this, and out is what? Q dot convection and this. Okay, so consider let us consider a small element of thickness dx. We have considered a small element of thickness dx, very small element. Now let us do the energy balance across this element. Okay, so energy balance, usually how do? We do energy dot in plus, if anything is generated inside the body, is equals to energy out plus energy stored in the system. Now we all know, we have assumed what? No heat generation. There is no heat generated inside the fin, so this is zero. And then we have assumed steady state. So that means there is no accumulation of energy inside the body, because if there is accumulation, temperature will change at that particular location. Okay, so this is zero. Now we are left with energy dot in is equals to energy dot out. Okay, now what is going in? Tell me. Q dot x is going in. Okay, what is going out? Q dot x plus dx plus q dot convection is going out. It is going out. Okay, I can also expand this as q dot x, and this I can write q dot x plus del by del x q dot x dx plus q dot convection. So what do I get here? This and this will get cancelled. This is del upon del x q dot x dx plus q dot convection is equals to 0. Is equals to 0. Okay, chalo. Now what can I do? I can expand this. How can I expand this? Del upon del x, it is conducted. What is it? Is only heat conducted that is coming in. So minus ka dt by dx plus, it is h area. Now always remember, this is perpendicular area, this is area of heat transfer, surface area. Okay, in this case it will not be same, and t at that particular location. Okay, whatever at now, this t, you see this t is changing. This t is changing. Here t is equals to t naught at this location. T is equals to t naught, and here the temperature would be something else. Let's say t dash. But this temperature is changing with respect to x. Okay, so this is t. What is there at the small element, and this is element this t will change, and t infinity, okay, is equals to 0, is equals to 0. Okay, now how can I write this? How can I write this? I can write d by dx. In fact, let me simplify it. Okay, now I can write minus k perpendicular area. What is we will talk about that anyway. Chalo. D square t by dx square dx plus h. Now what is the area? What is the area here? Area is, what is the area of heat transfer for this element? Area of heat transfer. You see the perimeter of this and dx. Okay, perimeter into dx. Okay, and t minus t infinity is equals to 0. Okay, so dx and dx can be cancelled. Okay, now can I write it as d square t by dx square plus hp? In fact, I am not writing plus hp. Let me write minus hp. And let me know if you have any problem with my final equation. T minus t infinity is equals to 0. Now tell me, do you have any problem with this equation? Tell me. No, right. Okay. Okay, very nice. I have just rearranged the equation. Okay, divide everything by k, a, and then I have also taken minus out. So I have just simplified it. Okay, now let me take this equation ahead. Okay. So my equation is d square t by dx square minus hp by k perpendicular area t minus t infinity is equals to 0. Very nice, very nice. Okay, chalo. Now let us assume that t minus t infinity is equals to theta. Okay, this thing I have assumed at theta. Okay, what dx? Dx is cancelled, no? Okay, chalo. Chalo. ठीक है, I have assumed it theta. Now if I differentiate this dt with respect to dx, now you see T infinity is independent of x. Bhaiya, T infinity is the temperature of fluid. Whatever temperature the air is there, it is not, it is, T infinity is basically undisturbed temperature of the fluid. It is not affected by whatever heat transfer. You know the concept of thermal reservoirs, right? So air is a thermal reservoir. Whatever heat is absorbed by the air, the temperature of air will not change. Okay, the temperature of air will not change. So T infinity is constant. So it will be dt by dx, or T infinity is constant, so it will be 0, and dt by dx is equals to d theta by dx. Okay, also I can do it one more time. D square t by dx square is equals to d square theta by dx square. Okay, and one more assumption I am taking, that m square is equals to hp upon ka. Hp upon ka, that is one more assumption I am taking. Now let me substitute it here. So d square theta by dx square I can write. Yes, I can write this. Minus, can I write m square, and can I write theta is equals to 0? Is it okay for you people? Yes, very nice. So if it is okay for you, now this is a second order differential equation. Second order differential equation. Let me see if I have written it already. Okay, yeah, I have written it later on, but we will talk about that. Okay, so this is a second order differential equation, and the solution of this equation is theta c1 e to the power mx plus c2 e to the power minus mx. Now this is my solution of this differential equation. Yes, this is non-linear. No, this is not linear. This is not linear, Baba. This is non-linear. You see? Okay, this is linear. Yes, yes. Sorry. Okay. Chalo. Yes, that is the solution. Okay. Chalo. Now, similarly, what we did earlier. Okay. What did we do? We had a solution. We had a temperature distribution equation. Now we need to find out C1 and C2. We need to find out. So what is our objective? Objective is to find out C1 and C2. How do you find out C1 and C2? How do you find out C1 and C2? Yes, we will apply boundary conditions. Boundary conditions. Okay. So we need to define boundary conditions. Now, 1 second. Okay, chalo. So what is my equation? D square theta by dx square minus m square theta is equals to 0. This is my equation. Solution for this equation is theta c1 e to the power mx plus c2 e to the power minus mx. I wrote minus there or not? Yes, minus I wrote there. Okay, chalo. Now, boundary conditions. Boundary conditions I need to find out. Okay. So let us say first boundary condition. Boundary condition first. So what is the first boundary condition? Look, I know that whatever I am doing at this surface where x is equals to 0, I need to maintain t is equals to t naught. I am sure about this. I am sure about this. So that is my first boundary condition. At x is equals to 0, t is equals to t naught. Very nice. Okay. So theta that I assumed, what was it? T minus t infinity. Okay. Now at x is equals to 0, when x is equals to 0, theta is equals to theta naught, t naught minus t infinity. Okay. This much is clear. Yes. Now what will I do? Let me apply this boundary condition here. Okay. So theta, this boundary condition. Okay. This one. Okay. So theta at x is equals to 0, applying boundary condition at x is equals to 0, theta is equals to theta naught. Okay. So theta will be theta naught. Okay. C1 e to the power mx plus C2 e to the power minus mx. Okay. Now we all know e to the power 0 is equals to 1. Okay. So I need to put 0 here. I need to put 0 and 0. So this will become as theta naught C1 plus C2. So whenever you use this boundary condition, this will be your equation A. Okay. Is this clear? Okay. Now we have two constants C1 and C2. So I need one more boundary condition. Okay. So boundary condition second. Now second boundary condition will depend. It will depend on the type and design of fin. What kind of fin you are taking? Type and design of fin. Okay. So first boundary condition will remain same. Equation A will remain same. Look. This equation will remain same. This equation will remain same. First boundary condition, which is either this or this. Okay. This will remain same and equation A will remain same. Now the boundary condition of 2 will vary. Boundary condition 2 will vary depending upon the type of fin that you are using. Okay. Chalo. Now, okay, this I don't need. This is what is the summary that we have done till now. Okay. So this is my differential equation, and this is the theta that I have assumed, and m I have assumed this. Okay, m key unit you will get at when put the units and cancel the units, you will get 1 by m. Now this is the solution of this differential equation, and this is the common boundary condition that I have already showed you. And second boundary condition depends on the design of fin. Okay, and by using first boundary condition, I have already gotten the equation C1 plus C2. That is your equation A. This is what we have discussed till now. Is it clear? Okay, chalo. Now let's move ahead. Now I need second boundary condition. I need second boundary condition. So what will I do? Okay, that we will see that later. But first I should know one more thing. What? I know that m square is equals to hp upon ka. But m I can write under root hp by ka. So h and k will be given in question. But I need to find out p by a. Now two types of fin can be asked in question. Rectangular fin or pin fin. So if it is rectangular fin, so we all know what is the parameter. What is the perimeter? Perimeter is 2b plus this. Okay, this is, and area is b into this. Okay, so this is the area. Conduction will happen only in x direction. Conduction will happen only in x direction. Okay, so only from here it will happen. And what is perimeter? 2b by delta. Okay, so we can use this. Now also what we can assume, if b is much greater than, if b is much greater than delta, if b is much greater than delta, so I can neglect delta. I can neglect delta. Okay, I can neglect delta. Chalo. What about pin fin? Pin fin again, perimeter by area. Perimeter is pi d. Area is pi by 4 d square or 2 pi r, whatever you want to call it. And when you cancel this, perimeter per unit area is equals to 4 by d. Now these things you can solve it there itself, but if you remember, it will save some time for you. It will save some time for you. Okay, so you can calculate p by a from here. H and k you will be given in question, or you may need to find out any one of them. So you can calculate m like this, because m you will be calculating very frequently. M you will be calculating very frequently. Okay, is it clear? Now let us move on. Let us move on to the second boundary condition, that depends on the design of the fin, what kind of fin you are using. Now first case is infinitely long fin. Infinitely long fin. So what is happening, sir? This is your body. This is your body. Okay, and this is your fin. This is your fin. Now this fin is very long. Is very long. Okay, so here I know, one second. At this surface, I know x is equals to 0, t is equals to t naught. T is equals to t naught. Okay. But when this length is increasing, conduction is happening, convection is happening, conduction is happening, convection is happening. Okay. Now, when your length is infinite, that means you are going to infinite length. That means all the heat transfer will be given away to the environment. So what will be the temperature here? Tell me. What will be the temperature? Yes, very nice. T is equals to T infinity. All the heat is rejected because infinite length, no? So all the heat is rejected, and at the end, at this point, x is equals to infinity. So length is infinity, and T is equals to T infinity. T is equals to T infinity. Very nice, very nice. So now what will we do? We'll start with the basic equation. What is the basic equation? By d, ये आपको, you should remember this as it is. I have solved you, but you need to solve it as many times कि आपको ये ऐसे ही याद हो जाए. Okay, this is my differential equation. Solution. What is the solution of this? By theta is equals to c1 e to the power mx plus c2 e to the power minus mx. Now I need to find out c1 and c2. I need to find out c1 and c2. Yes, sorry, m square. Okay, so I need to find out C1 and C2. Okay, so I'll apply boundary condition. Boundary condition first. First boundary condition, we all know that at x is equals to 0, t is equals to t naught. Okay, and I have already told you theta is equals to theta naught, and the equation that you get here is theta naught C1 plus C2. This is what I already know. Okay, equation A. Yes. Now the time is there that I need to give the second boundary condition. Second boundary condition. So boundary condition 2. We all know what? X is equals to infinity. T is equals to T infinity. Now what is theta? Theta is equals to T minus T infinity. So how much will be theta in this case? How much will be theta in this case? 0. Yes, it is 0. Theta will be 0. Okay, so now let me write theta, let me apply this equation, let me apply this boundary condition in the solution. Okay, chalo, theta is equals to 0 c1 e to the power mx m infinity plus c2 e to the power minus m infinity, okay. So e to the power infinity, this is what? E to the power, any power of infinity of anything will be equal to e to the power infinity. E to the power infinity. Yes. अरे किसी की पावर infinity हो, it will be infinity. और e to the power minus infinity is 0. Yes, very nice. Okay. So I'll get 0 is equals to C1 infinity plus 0. Okay. So C1 is equals to 0 upon infinity. 0 upon infinity. So anything divided by, and if the numerator is 0, so whatever you divide, whatever number you divide with, it will be 0. C1 is equals to 0. Okay, C1 is equals to 0. Now what can I do? What can I do? I can put C1 here. I can put C1 here, and C2 is equals to theta naught. C2 is equals to theta naught. So now I got C1. Now I got C2. I can place it here. Okay, I can place it here. Just 1 second. So I'll put it here itself. Okay. So let me putting C1 and C2 in the solution. Okay, so ये तो थीटा ही रहेगा. This is theta itself. C1 is 0 plus theta naught e to the power minus mx. So theta upon theta naught is equals to e to the power minus mx. This is basically your temperature distribution equation. Why? Theta is equals to T minus T infinity, and theta naught is T naught minus T infinity is equals to e to the power minus mx. E to the power minus mx. So this is your temperature distribution equation for infinitely long fin. Is it clear? Okay, chalo. So this is my temperature distribution equation for infinitely long fin. For infinitely long fin. Okay. Now I need to find out the heat transfer. Okay, I need to find out heat transfer. So what is the heat transfer? Heat transfer is this. Okay, I need to find out this. How much heat is getting transferred at x is equals to 0. Okay, at this body, at x is equals to 0, how much heat is conducted? How much heat is coming in? How much heat is conducted in the body? Q dot conducted in the fin. So whatever is conducted will either be convected here or convected here. Okay, and in the whole body it will be conducted. Okay, okay. Yes, I can. Yeah, this is the last slide. Any doubts, Sahil? Okay, chalo, let us move on then. Okay, so in order to find out heat transfer, I need dt by dx at x is equals to 0. dt by dx at x is equals to 0. How do I find out? Look, this is my temperature distribution equation. Okay, so can I say theta is equals to theta naught t to the power mx? Or can I also say t minus t infinity is equals to t naught minus t infinity e to the power minus mx? So from here I can find out temperature. T infinity plus T naught minus T infinity e to the power minus mx. Now I need to find out dt by dx. So yeah, this is constant only, this will be 0. Now I need to differentiate this. So it is T naught minus T infinity e to the power minus mx. And what will you get here? What will you get here? Tell me very quickly how much, what is the differentiation of this? Yes, very nice. Minus m, minus m. So dt by dx is equals to minus m. Now can I write theta naught here? Yes, I can write theta naught e to the power minus mx, minus mx. Okay. Now in order to calculate heat transfer, what do I need? I need dt by dx at x is equals to 0. At x is equals to 0. So what will I do? By minus m theta naught e to the power minus m0, minus m0. Okay, so what is the value of this? What is the value of this? E to the power 0. You will get dt by dx at x is equals to 0 is equals to minus m theta naught. Yes, that the value is 1. Okay, so this is what I have gotten. Okay, now I can just insert it here. I can just insert it here. So if I need to find out qx of fin, which is conduction heat transfer, minus ka, and this is what I got, minus m theta naught. Okay, we have calculated dt by dx at x is equals to 0 is equals to minus m theta naught, minus m theta naught. Okay, now this is plus ka. M is what? M is under root hp by ka, and this is theta naught. Okay, so if you cancel this, you will find out under root hp ka theta naught. Let me write theta naught in terms of temperature because it is more convenient for us. More convenient for us. Okay, because we know things in terms of temperature. Okay, T naught minus T infinity. And this is how you can calculate heat transfer in infinitely long fin. Infinitely long fin. Okay, unit is watts. Unit is watts. Is it clear? Yes, very nice, very nice. Chalo, let us move on to the next case. So filled with finite length and insulated tip. What does it mean? What does it mean? Look, this is your body, whatever body it is, engine body or whatever, and you have taken a fin here. Okay. Now, finite length means, look, here I know, here I am very sure x is equals to 0, t is equals to t naught. And when finite length means x is equals to L, so now tip, this tip is insulated, insulated, insulated. That means because it is insulated, so Q dot conduction will be equal to 0. Q dot conduction will be equal to 0. Now what is Q dot conduction? Minus Ka dt by dx at x is equals to L is equals to 0. So at x is equals to L, dt by dx is equals to 0. dt by dx is equals to 0. And what do we know about this? Here you will also get the maximum temperature. Here, yes, no heat transfer, but the temperature will be maximum because this is the condition. No, at dt by dx means the variation of temperature with respect to x, where dt by dx is equals to 0, you will get Tmax as well. So you already know the location of your Tmax. Already know the location of your Tmax. Okay, chalo. Now, so let's start from the beginning. Let us start from the beginning. Okay, so what is the, write the equation again and again and again. Okay, so differential equation was d squared theta by dx square minus m squared theta will be equal to 0. What is the solution of this? Solution is theta is equals to c1 e to the power mx plus c2 e to the power minus mx. Okay, chalo. Let us apply boundary condition. Boundary condition. And first, so we already know. No, first is x is equals to 0, t is equals to t naught. Okay, and theta is equals to theta naught, and we have gotten theta naught is equals to c1 plus c2. This we already know. No discussion needed to be done for this. Okay. Now the second condition. Second boundary condition is. Second boundary condition is at x is equals to L, dt by dx is equals to 0. Can I also write it as d theta by dx is equals to 0? Any problem? Okay, very nice. Before we move ahead, let me tell you one more thing. Look, if nothing is given in question, by what type of fin, we will cover 3 cases of fin. Okay, next will be uninsulated tip. But if nothing is given in question, then you assume that this is the case that you have to assume. Okay, if otherwise they will say infinitely long fin. Okay, otherwise they will specifically mention something. If nothing is mentioned, then you will assume that it is this fin, and you start making calculations according to this. So it's very important that you focus on this. Okay, it's very important that you focus on this. Okay, now chalo. Now I need to find out d theta by dx, and I need to put it is equals to 0. Then I will get a c1 and c2. Okay, then only I will get c1 and c2. Okay, chalo, theek hai. So differentiate this. Let's say d theta by dx is equals to m c1 e to the power mx, and because minus m will come outside, so let me write it here, minus m c2 e to the power minus mx. Is it okay? Is it okay? Chalo, theek hai. Now at x is equals to L, now apply at x is equals to L, d theta by dx is equals to 0. Okay, so 0 is equals to mc1 e to the power ml minus mc2 e to the power minus ml. Okay, तो भैया देखो m तो you can take common and it will go out and it will get cancelled. What I am left with? One second. Okay, ठीक है. I have enough space. I can go to the next slide. Okay, chalo. Now I am left with C1 e to the power ml minus C2 e to the power minus ml is equals to 0. This is what I am left with. Okay, is it clear? Is it clear? Chalo, theek hai. Okay, now I need to find out C1 and C2. Okay, now because one equation, one unknown, but I already have one equation. What? Theta naught is equals to C1 plus C2 by applying boundary condition first A. So can I say C1 is equals to theta naught minus C2? I can say this, right? So let me substitute it here. Theta naught minus C2 e to the power ml minus C2 e to the power minus ml is equals to 0. Okay. Now you can take C2 out, you can simplify it, and C2 you will get theta naught e to the power ml upon e to the power ml plus e to the power minus ml. This is what you will get. C2. And when you substitute C2 here, you will get C1 is equals to theta naught e to the power minus ml, and the denominator will remain same. Denominator will remain same. Is it okay? Okay, chalo theek hai. Now let us put that. So what was my general equation? Theta is equals to C1 e to the power mx plus C2 e to the power minus mx. So that was the whole purpose of calculating C1 and C2, because I need to put this here. So let's substitute it here. Okay, theta is equals to C1 is theta naught e to the power minus ml e ml plus minus ml e to the power mx plus C2. C2 is theta naught e to the power ml upon e to the power ml plus e to the power minus ml e to the power minus mx. Okay, is it okay? Chalo. If this is okay, then I know one thing. I am not going to simplify that in that way. What will I give you the equations? Because it is not required. Actually, it is not required. We know sine hyperbolic x is equals to e to the power x minus e to the power minus x by 2, and cos hyperbolic x is equals to e to the power x plus e to the power minus x by 2. Okay, and 10 you can simply divide them, and you will find out e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. So I can simplify my equation in terms of cos, and sine, Okay, so if I will change e exponential into cos and sine, I will get that theta, and theta naught you can take out. Theta naught from this equation you can take out. Okay, so theta upon theta naught is equals to cos hm L minus x upon cos HML. This much is more than enough for you. If you know what are the boundary conditions, you do not even need to remember the constant. You do not even need to remember this. You do not need to remember this. Only the differential equation, only this differential equation, solution, and these two boundary conditions. After that, you need to know this temperature distribution equation. Is it clear? Chalo, very nice. So what do I get? I get theta upon theta naught is equals to cos hm L minus x upon cos HML. And I can also write t minus t infinity upon t naught minus t infinity is equals to cos hm L minus x upon cos HML. Okay, now this is my temperature distribution equation. This is my temperature distribution equation for fin with finite length and insulated tip. In only these conditions you can use this boundary condition. Okay, is it clear? Is it clear? Chalo. Now, so as we know, this is my boundary, this is my temperature distribution equation. Now again, like we did previously, I need to calculate heat transfer. Okay, so I need this. How much heat is getting transferred at x is equals to 0? I need to calculate this. So what will I do? I need to find out by t minus t infinity. I need to find out dt by dx at x is equals to 0. This I need to find out so that I can substitute that in the heat transfer equation and I will calculate the heat transfer. You in question you need to directly calculate by using that formula. Okay, chalo. So I can write T naught minus T infinity cos h m L minus x upon cos h m L. Okay. I can also write T is equals to T infinity plus T naught minus T infinity cos h m L minus x cos h m L. Okay. Now let me differentiate. dt by dx. भाई ये तो जीरो ही हो जाएगा प्लस it will remain same because it is in product, but it is a constant. Okay. Now, can you tell me what is the differentiation of cos HML minus x? Cos HML minus x. Can anyone tell me? Cos hyperbolic HML minus x. Sin HML minus x. Sin HML L minus x into m or into minus m? Yes, minus m. Very nice. And this is constant. This is same. Okay. So what can I do? Can I write dt by dx is equals to minus m theta naught. This is theta naught. Yes. Sin h m L minus x upon cos h m L. I can write this. Any doubt? Anyone? Any problem? Sahil, is that okay? Okay, chalo. Chalo, ठीक है. Okay. Chalo, now what do I need? I need this. So can I do dt by dx at x is equals to 0? What will I get? Minus m theta naught sin HML upon cos HML. So can I write minus m theta naught tan HML? Is it okay? Is this okay? Chalo. Now this is what I need. So let's move ahead with this. I need to put this here. So what do I get? I get dt by dx at x is equals to 0 is equals to minus, how much is it? Minus m theta naught tan HML. This is what I have found out. Okay, so let me put this here. Okay, so q dot fin is equals to minus ka, and this is minus m theta naught tan HML. Okay, so this is ka. M is what? M is under root HPKA theta naught tan HML. So under root Ka is there in the denominator. Numerator is Ka. So you will, when you will divide this, you will get HPKA theta naught tan HML Q of fin. And this is given in watts. So whenever you see a question for fins and they will ask heat transfer, use this equation. H will be given, K will be given, perimeter and area I have already told you the formulas. Theta naught is T naught. T naught matlab base temperature. Base temperature will be given to you. By theta is what? T naught minus T infinity. So T naught is the base temperature, base material temperature, something like this they will given question. Base temperature, and T infinity is ambient या fluid temperature, which will also be given in question. Okay, calculate m. M is equals to under root HPKA. So P by A you know. Okay, I have given you the formulas, and length also you know. You can calculate heat transfer. Is this clear? Is this clear? Okay, very nice, very nice. Chalo. Now the last case is fin with finite length and uninsulated tip. Now this case is very rarely asked. It is very rarely asked. Most frequently, case second is asked. Most frequently. So this is the first priority. Second priority is case first. And third is very rarely it is asked. Chalo. Fin with finite length and uninsulated tip. Okay. So we already know that the differential equation is d square theta by dx square minus m square theta is equals to 0. Okay. This is my differential equation. Solution of this equation is this. Okay. Boundary condition I already knew. Okay. And the second boundary condition is simple. Second boundary condition is what? By this is my base material. Okay. Now this is my fin. Now we know that here at x is equals to 0, t is equals to t naught. But at this point, t is equals to, I'm sorry, x is equals to L. What is happening here? You see, look, conduction heat transfer is happening like this. And it is steady state conduction. Steady rate of heat conduction, rate of heat transfer will remain same. Rate of heat transfer will remain same. Okay. So at this point, here, whatever is conducted at this point, at this location, whatever is conducted will be, because here we have fluid. Here we have fluid. So Q dot conduction is equals to Q dot convection. So now you can write the formulas minus Ka dt by dx like this. What can you do? Minus Ka dt by dx at x is equals to L is equals to H area. Now area will remain same in both cases because area is, this is also the same area which is in contact with the fluid, and it is also conduction area. Okay, then T at this L minus T infinity. Okay, so you can find out area cancelled, dt by dx at x is equals to L is equals to H upon K theta naught minus. Okay, something like this you can do, but it is not required. Then a lot of derivation needs in this. Okay, a lot of derivation needs in this, and but that again is not required for us. And eventually, even after that, we will reach to a very complicated formula. We will reach to a complicated formula, and what we do in order to simplify the analysis, what will we do? We use the same temperature distribution as we used in, I'm sorry, this is uninsulated tip. One second. Yeah, this is uninsulated tip. It is my mistake. Uninsulated tip. Okay. So we will do the same thing or what we did earlier. So this was my temperature distribution equation. Only instead of L here and L here, I am using LC, which is called as corrected length. Corrected length. Okay, it is called as corrected length. How we will calculate corrected length, we will see in some time. Okay, now this is my temperature distribution equation. This is my heat transfer equation as same only. Okay, and this is the formula that we calculated for insulated tip. Only here I have replaced again L by LC. Okay, now how do you calculate LC? LC is L plus A by P, area by parameter, and we have already calculated bhaiya perimeter by area yaar. Perimeter by area we have already calculated earlier for rectangular fin and pin fin. So the same thing you can use here. Okay. But here just take care, you need to use LC. Very rarely this type of question will be asked, but even if it is asked, this much information is more than enough to solve it. Okay, clear? Chalo. There is no need of doing the derivation, and anyway, even if we do the derivation, no, in GATE exam we do not use that formula that we get after derivation, so there is no point. Okay, chalo. Next is fin efficiency. So efficiency, we always know what is efficiency of anything. How close is it to the ideal condition? How close it to the ideal condition? So fin efficiency is equals to Q actual. What is the actual heat transfer? And what is the maximum heat transfer? Maximum heat transfer, how much it can happen? Now you see here, look. This is your material. This is your base material. Okay. Okay, I don't need that. So I don't draw this. Chalo. Okay. So this is my fin. Now, here look, here the temperature at this point at x is equals to 0, temperature is T naught, which is the maximum temperature, Not maximum temperature, but usually if because heat is going out. First of all, heat is conducted here, Q dot conducted, and heat is convected as well, Q dot convected here. Okay, so what we do is we say that heat is basically temperature. If here temperature is T naught, then temperature is reducing as you are going here, So let's say it is T1, so T naught is greater than T1 for first case, usually. Okay. So if T naught, when will you get the maximum heat transfer? You see temperature is reducing. But what if the whole fin everywhere at this point, everywhere, if the temperature is T naught, so the same amount of heat will base temperature. Everywhere we have base temperature. Then you will get the maximum heat transfer. So Q dot max is calculated, is defined by assuming the entire fin, is at room temperature or base temperature. It is called as root temperature. Base temperature T naught. Okay, we assume that it is at T naught. Now, when will this happen? When will this situation can happen in any way? It will happen only. It is possible where. So, in order that the temperature is T naught everywhere, conductivity will be very high or very low. Would the conductivity will be very high or very low? It is possible. Tell me very quickly. Would the conductivity be very high or very low? Possible only when thermal conductivity is no. Thermal conductivity we assume as constant. No, we assume constant. But because temperature is reducing, so heat transfer will change. Okay, so there will be heat transfer. Okay, you see what is this? Q dot conduction is equals to minus Ka dt by dx. So this is changing. Temperature with respect to dx is changing. Okay. So it can only happen. It can conductivity of the material. We assume that in the analysis, we assume that conductivity is not changing with respect to x. Okay. Now, conductivity must be infinite. Conductivity must be infinite. Very, very high conductivity. So that the heat transfer conductivity will be infinite. So that there will be very fast heat transfer. Okay. And if the heat transfer will be very fast, that means you will not be able to get enough time for the reduction of temperature. Okay, heat will flow very fast in the body. Heat will flow very fast in the body. It is possible only when thermal conductivity K is infinite, but it is not possible anyway. So it is the ideal case. It is the ideal case. Okay. So how do I calculate Q dot max? How do I calculate Q dot max? H into area. Now temperature T minus T infinity is there. This is the normal temperature. But Qmax will be calculated by assuming it as T naught. T naught. Okay. So this is your Qmax. Qmax, heat transfer by convection. Okay, chalo. Now, so how do you calculate fin efficiency in the first case? Fin efficiency in the first case, which is infinitely long fin. Now I know that efficiency of fin is defined as Q dot actual upon Q dot maximum. Now I know. Can you tell me, we have just calculated heat transfer for infinitely long fin. What was the heat transfer for infinitely long fin? What was the heat transfer for infinitely long fin? Under root, tell me very quickly. Under root, yes, root h p k a t naught minus t infinity. Okay. And this is Q max is h area t naught minus t infinity. Okay. So this will get cancelled. Now this area, if you remember, this area is perpendicular area with heat transfer. Okay. Because we already, when we defined the equation h a q convection, when we started, q convection is equals to t minus t infinity. Okay. And area we took as perimeter by dx, and dx was cancelled. So this area, we know it is the perpendicular. It is the perpendicular area, conduction area. Okay. And this area is different. This area is perimeter into dx. Perimeter into dx. Now, because we are talking about the whole fin, so it is P into L. P into L. Okay. So I can write, what can I write? Under root h p k a perpendicular upon h p into L. P into L. So HP and HP will get cancelled, and whatever you get, what you get? Under root Ka upon HP into 1 by L. So this is what? 1 upon ML. Okay, because M is equals to under root HP by Ka. Is it clear? Okay, very nice. Now also with this formula, let me write this formula one more time, is equals to under root Ka upon HP into 1 by L. 1 by L. Okay. So you see, efficiency is directly proportional to thermal conductivity, root of thermal conductivity. Okay. It is inversely proportional to heat transfer coefficient, and it is directly proportional to area by perimeter. Area by perimeter. Okay. This you keep in mind. We will discuss this later. And 1 by L. Okay. This is efficiency. Okay. Chalo. Now, what about fin with finite length and insulated tip? Insulated tip by efficiency of fin is defined as Q dot actual upon Q dot maximum. And can you tell me what is Q dot actual for this case? I will write this H area T naught minus T infinity. Okay, tell me very quickly. You will get a revision again here itself. What is the heat transfer actual in this case? Okay, let me read it. Under root H P K A, yes, square root H P K A. That seems correct. Yes, that seems correct. Right. For both Sean and Silent, it is correct. Okay. Then T naught minus T infinity, which is theta naught as well, and tan HML. Tan HML. Yes, right. That is correct. Okay. So HPKA and T naught minus T infinity tan HML. Okay. So again, this I can cancel. Length I will still be there. HP and HP will get cancelled, and I'll get tan HML upon ML. Okay. So efficiency of fin is equals to tan HML upon ML. Okay. This is how we can calculate efficiency in this particular case. Okay. Now I am not going to discuss for the third case. Why? Why? Case third. Finite length and uninsulated tip. So you can directly calculate. You can directly calculate by replacing tan HMLC, yes, upon MLC. You can calculate by this. Simple. Okay. Chalo. Let us move on to the last topic, which is fin effectiveness. Then we see whatever questions they have asked till now. Okay. Chalo. So fin effective, it tells us how much percentage increase. By effectiveness is what? If I was doing something and then I have, for example, changed my routine, or I have changed my diet, or whatever it is. For example, I am going to gym, and my exercises are not very effective, so I have changed the diet. So that change in diet is how effective. So how do I compare this? How do I compare ki how was I, what was my performance before that diet, and what is my performance after the diet? Okay, so effectiveness is basically how it is defined as the ratio between heat transfer with fin and without fin. Okay, effectiveness will tell you that now what is the heat transfer that is happening with the fin, and what was the original heat transfer without fin. Without fin. Okay, this is the effectiveness, and it is not recommended that you use fin if effectiveness is less than 2. Otherwise there will be a cost involved in manufacturing the fins, adding the fins, fin material and other phenomena. But if effectiveness is not very high, it is not greater than 2, then what will happen? A little heat transfer has increased by using fin, but a lot of cost you have already given in order to design that fin, in order to manufacture that fin. So effectiveness must be at least greater than 0. Okay. So now let us try to calculate. You see, if the fin is not there, for example, now fin is there, so heat conduction is happening like this, and convection is happening like this, q dot convection. Okay, with fin. But if fin was not there, then in this area, I am talking about this area only. There is a different fin. I do not care about that right now. I am talking about only one fin. So now whatever heat transfer is happening now because of this fin, the same heat transfer, I mean, that is the only area that is available for heat transfer. Only q dot convection will happen without fin. Okay. So how do I compare this? How do I compare now? Infinitely long fin. So effectiveness is equals to Q with fin and Q dot without fin. Okay. So what is with fin? With fin is with fin is H P K A under root T naught minus T infinity upon, without fin is H area T naught minus T infinity. What is the area? This area, Baba, this area, this area. Okay. So now I can write under root HPKA T naught minus T infinity. In fact, I can cancel it here. Okay. I can cancel it here. Okay. Because again, you see area is same. Area is same. Here also for conduction, you see this is the perpendicular area. One second. This is the perpendicular area. And now what is this area? This area is again perpendicular. So here the heat transfer area for conduction, perpendicular area for conduction is same as heat transfer area of convection. Is it clear? Any doubt? Anyone any doubt with this? Okay, ठीक है. So what can I do here? What can I do? I can cancel this. Okay, and HA. So now what do I have? I have H and A will be cancelled. I have KP upon HA. KP upon HA. Okay, KP upon HA. Okay, chalo. Effectiveness of fin. Effectiveness of fin for infinitely long fin. Okay, chalo. Now, fin with finite length and an insulated tip. An insulated tip. Again, what will we do? Effectiveness of fin is equals to Q with fin and Q dot without fin. Okay. So we again, I know what is with fin. Under root HP KA tan H ML T naught minus T infinity. Okay. And here we have HP. One second. Here we have H A T naught minus T infinity. Okay. So this and this will get cancelled. And when you further cancel H and area, you will get tan HML upon under root HA by KP. HA by KP. Now do not confuse it with M. M is equals to under root HP by K. Okay. So it is not M. It is not M. PK by HA. Yes, PK by HA. Yes, 10 HML. Yes, that is correct. Okay. Efficiency of fin. Okay, in this particular case, Now, finally, conditions for justified fin. Now, you cannot use fin everywhere. Okay, you can only use fin when after designing that fin and manufacturing that fin, when that fin is attached to your surface, it is giving you at least sufficient effectiveness. Okay, it has increased the heat transfer to a significant amount. Otherwise, if it is increasing the heat transfer with a very small amount, then that means you are getting very less advantage by using so much of cost. Then it is not effective. Then the use of fin is not justified. Okay. Now, in what conditions the fin is justified? So, as we all know, we can see in this diagram, in this equation, effectiveness of fin is proportional to under root Kp upon Ha. So, fin material, you see effectiveness, fin material, whatever material you are using of fin, whatever material of fin that you are using, So whatever your fin material is there, its conductivity must be high. Then only it will be able to increase the heat transfer by a significant amount. If the conductivity of material is low, that means whatever heat is conducted here, it is not going to go inside matlab, it will not be able to flow inside the material. If it will not be able to flow inside the material, it will reduce convection heat transfer as well. It will reduce convection heat transfer as well if the conductivity is low. Okay, if the conductivity is low, then it will reduce the heat transfer as well. Okay, so conductivity must be high of the material. Now second condition, heat transfer coefficient. Heat transfer, for example, this is my base, this is my base body. Okay, as I have told you earlier itself, now it is dipped in water, it is dipped in water. Okay, now water has already taken the heat away with a very fast rate, because h of water, whatever heat is conducted here, it is given to the water. So heat q conduction is equals to q convection. Okay, now because the conductive heat transfer coefficient of water is anyway very high, so it is sufficient enough to take away all the heat. Now, even if you are using fins, the heat transfer, because there is a capacity only, no, to take the heat away. It cannot take the heat away if it is not generated inside. Okay. So it is already taking so much heat. Even if you are using fins, the heat transfer rate will not increase to a significant amount. So you use only fins when heat transfer coefficient is less. For example, if it is not dipped in water, in fact, it is in normal environment. For example, it is surrounded by air. So air heat transfer coefficient is low. Air heat transfer coefficient is much less than water. So with air, it is justified. With air, you can use this. With water, it is not justified. With water, I am not saying with water. I am just saying in this particular condition, I am saying, okay, sometimes even with water, you need fins. But what I am trying to say is, if the heat transfer coefficient is already high, that means that fluid can take away more heat. And even if you are using fins, it will not increase the heat transfer significantly. Okay, it will not increase the heat transfer significantly. So there is no point. Are you able to listen to me? Because I think I lost the connection. Okay, okay. Chalo. So basically, if the heat transfer coefficient is already high, do not use the fins, because it is going to take a lot of cost, but the heat transfer will not increase significantly. So use fins only when heat transfer coefficient is low. Okay. Then finally, last we have when perimeter by area ratio is also proportional to perimeter by area. So this ratio must be high so that effectiveness must be high. Okay. Now, how can you increase this ratio? Perimeter per unit area. Perimeter per unit area. So it will only be if you can increase this by using thin fins. Very small thickness fins. Okay, thin fins and more, because you are using thin fins, because you have reduced, because you have increased this P by area. So now you are, and it can be increased by using very thin fins. So now by using thin fins, what you can do, you can use more numbers of fins. Yeah, yes, Sean, that is correct. You can use more number of fins very close to each other, very close to each other. Okay, so now, for example, in a particular area, you were using 10 fins earlier, but now because your fins are thin, you can use 20 fins. Now, because 20 fins, what has happened? The area for heat transfer is increased. Area for heat transfer is increased. Again, this area is not area for heat transfer. This is perpendicular area. Okay. Now, area for heat transfer is increased. Okay. So, area of heat transfer is increased. That means convection heat transfer will increase. Okay. Chalo. Is it clear? Is it clear? Okay, very nice, very nice. Chalo, let us move on to few questions. Now, the concept are covered for fins. Concept we have already covered for fins. Let us take few questions that have been asked. Okay, this a fin has 5 mm diameter. Year 2010 2-mark question. We have a fin. How do I draw a fin? Now they are not giving us length, width, or height. They are giving us diameter. That means it is a, what is it? It is a rectangular fin or pin fin. Yes, it is a pin fin. It is a pin fin. Okay. Okay. Diameter is 5 millimeter and length. Now you see they have given us the length. That means it is the case of finite length. It is the case of finite length. Now the thermal conductivity of the fin. Thermal conductivity is also given. Thermal conductivity of fin is equals to 400 watt per meter Kelvin. Okay. One end of the fin is maintained at 130 degrees Celsius. So this, at this x is equals to 0, it is maintained at T naught, which is 130 degrees Celsius. And it is remaining surface exposed to ambient air. Remaining surface is exposed to air, and air has a T infinity of 30 degrees Celsius. 30 degrees Celsius. Now also convective heat transfer coefficient is given 40 watt per meter square Kelvin. Now the heat loss from the fin is heat loss from the fin. Now look, they have not given insulated tip or uninsulated tip. Now if they have not told us anything, always you will take fin with finite length. Finite length is given, yes, but insulated, uninsulated is not given. So you will take insulated, hamesha. Finite length, otherwise they will give some extra information. Okay, finite length with insulated tip. Okay, now I need to find out Q dot heat transfer is equals to, can you tell me what is it, the formula? Under root HP Ka tan H ml T naught minus T infinity. Now I know more or less everything. Okay, H I know, perimeter and area I need to calculate. Perimeter and area I need to calculate. Okay, so let us calculate that. Perimeter will be 2 pi r, 2 pi r. Okay, or pi d also you can say. Okay, so it is equals to 2 pi into 0.0025. Okay, tell me how much is this? Area is equals to pi r square. So pi into 0.0025 square. How much is perimeter? How much is area? Tell me. Perimeter, why is the calculator? Perimeter is, yes, okay, ठीक है. Perimeter is 0.0157 meter. Area, how much is area? 1.96 into 10 to the power minus 5 meter square. Okay, so now can you calculate m? M is equals to under root HPKA. So m is equals to under root h is given as 40, perimeter is given as 0.0157. I have calculated. Conductivity is 400, and this is 1.96 into 10 to the power minus 5 meter square. How much is m? How much is m? How much is m? Yes, Sahil has calculated, Sean has calculated. M is equals to 8.941 by meter, or meter to the power minus 1. Okay. Chalo. Conductivity is 400. Area is 1.96 into 10 to the power minus 5. Okay. Into T naught minus T infinity. T naught is 130. T infinity is 30. तो 100 हो गया ये. Into 10 hyperbolic m is 8.97 into length is 0.1. 0.1. Okay, so you can calculate this. Hundred millimeter. Look, there is a problem here. There is a problem here. I do not think it is. चलो ठीक है. Let us calculate by 100 itself. Tell me 100 1 meter. No, ठीक है. Why do you think that? No, that is okay. We can calculate that. It's fine. I'm not saying LCV cannot calculate. But why are you thinking that it is uninsulated? No, the thing is that uninsulated type of questions are very rarely asked. Let us read the question one more time. Even exploit the conductivity transfer the heat loss from the finish. That's what I am trying to say. If nothing is mentioned, okay, what actually happens is why I am saying this. Key in the last years, in the previous years, what they have done, if they have not mentioned it, and after the gate exam, you will get the answer sheets. Okay, so in the answer sheets, what they have done is they have calculated it using the insulated tip mostly. Okay, so that is the reason that if nothing is mentioned, it is expected that you use finite with insulated tip. Okay, although yes, they must mention this if it is insulated, otherwise you should go to the general case. Okay, but anyway, let us assume ki bhai this was a question in which they have not mentioned. Otherwise we always have to go to the insulated case. If look, either they mention, that is okay. If they have not mentioned very clearly, then we should go with insulated. And I am not saying there is no rule as per this, but based on the previous paper analysis, that's what I am saying this. Okay, yes, they must mention. Yes, they must mention if it is insulated, if it is not insulated, if it is, look, if they have given the length, that means it is the finite length, we are sure. Okay, otherwise they cannot give us length if it is infinite. Okay, but the problem is insulated or uninsulated. So yes, they should give it, but because they have not given it and based on the analysis, that's what I am telling you. Okay, so you have calculated, and the answer that you have gotten is 4.91 you will get, and that is 5. Very nice. I mean, look, it is an objective question. So anyway, I think even for uninsulated, you will get the similar answer. Okay, you will get little bit up and down, but you in terms of objective question, it will remain same as itself. I thought like if it's insulated, Q is less than uninsulated. Yes. So if I do for insulated, it should be fine for uninsulated. Yeah, I guess so. I cannot comment on that. But basically, if it is a numerical answer type question, so it would matter. It would matter because even if some, like if there is a difference between the answers, then it could go wrong. Okay, because they do not see the method, they will only see the answer. Yes, that's what I am saying. It will not vary much. And since it is an objective question as well, it is not going to make any difference. Yes, for insulated it is 5. For uninsulated it is 5.04. So answer is almost same, no? Yes, yes, yes. But why I was saying that it is insulated, because I have seen the solutions of the previous year questions from the official gate solutions. Okay, so they are using insulated. So it is assumed, although it is not a rule, but it is assumed that if they are not giving anything, you will take the second case. Okay, chalo. Let us move on to the next question. Okay, we have already solved this. I left a space here to solve it on a separate piece of paper. But anyway, chalo, theek hai. Which one of the following configuration has the highest fin effectiveness? Now, I don't think I need to tell you this. Tell me very quickly. Tell me very quickly. Fin, thin, close. Yes, very nice. So we all know effectiveness of fin is directly proportional to thermal conductivity, inversely proportional to heat transfer coefficient, and P by A. So this you will get higher if fins are thin and closely spaced. Closely spaced. So very nice. A is the right answer. Chalo. Okay. Let us move on to the next question. Okay. Tell me very quickly the heat loss from the fin. Heat loss that is happening from the fin is 6 watt. Okay. So this is Q dot actual. 6 watt. The effectiveness of the and efficiency is 3 and 0.75. The heat lost from the fin, keeping the entire fin surface at base temperature. If you are assuming the entire fin is at base temperature or root temperature, then you have to find out heat loss. How much is heat loss happening? What do you do? What do you do? You will use effectiveness or efficiency? Yes, efficiency. Very nice. So efficiency of a fin is equals to Q actual upon Q maximum. Now Q maximum simply means that the entire fin surface is at base temperature. That is the assumption that we are assuming. Okay. So Q max is equals to 6 upon 0.75. And as Sahil and Sean have already calculated, it is 8 watts. It is a gate question itself. You see how easy it is. Chalo, next question. Okay, last question. An infinitely long pin fin attached to an isothermal hot surface. Isothermal hot surface का क्या मतलब है यहाँ पे? What do you mean by isothermal hot surface? So it is an isothermal hot surface. Whatever the surface is, it means its temperature will remain same. If it is an isothermal surface, that means the surface temperature, let's say, will remain same as T naught. Okay. Transfer heat at a steady rate of Q1. Okay. So let's say this we have fin, that this fin we are using. Okay. And it is transferring heat Q1. Q1 is getting transferred. The thermal conductivity, so this is 1. Okay. Now let's say if you are using a different fin, okay, the same heat you are transferring. Actually, it is Q2. Okay, now the thermal conductivity of fin material is doubled. Now K1, it has, let's say, K1, and this is twice of K1. Okay, while keeping everything else constant, the rate of steady state heat transfer from the fin becomes, so now it is Q2. So what do I know? It is a pin fin. So I know an infinitely long pin fin hai ye. So Q1 is equals to, yes, that is correct, Sahil. Very nice. Sean is also correct. Yes. HPKA T naught minus T infinity. Okay. And in Q2, let's say it is K1. Everything else is same. H is same, dimensions are same, but it is 2K now. That only the conductivity has changed. 2K1 area and T naught minus T infinity. Okay. So Q2 by Q1 will be equal to under root 2K1 upon K1. Okay. So when you cancel this, you will get under root 2. That is your answer. So these are the questions. These are very simple questions. Very simple questions come from Fin. Although I think this is the only questions they have asked. Try if GATE 2022 also you will get some questions. Okay. The other thing is now start solving practice questions. Fins is covered. Fins is covered. Okay. Everything we have covered in Fin, and now start solving Fin questions. Whatever questions you see, try solving it. If you have any doubt, ask me. Okay. So this is for Fins. Now, okay. So this is it. Now we will meet. I think next Friday. I hope. I don't know. I think the schedule will be same Friday, Saturday, Sunday, and we will go for. Now I'll tell you one thing. What we have done yesterday and day before yesterday, we talked about generalized. That time when we were talking about generalized heat transfer equations, then you see in the Fourier law, look, in the Fourier law, we have talked about steady state, we have talked about one dimensional, and we have talked about no heat generation. Okay. Now, when day before yesterday we were talking about generalized heat conduction, heat transfer, then what did we do? We talked about bhaiya three-dimensional, what will happen? We talked about when heat generation is also happening, but we did not touch the concept of steady state. Steady state is still remaining. So we have to go to see what will happen if unsteady, because everywhere that day we were assuming steady state heat generation, steady state no heat generation. Everywhere we were saying steady state. But what will happen if unsteady state will be there? Unsteady state means now what will happen? 1 upon alpha dt by d tau is not equal to 0. Temperature is changing with time. Temperature is changing with time. So this is unsteady state heat transfer. This is unsteady state heat transfer. So we will start understanding this in the next class. Okay. Unsteady state heat transfer. Here we will understand the concept of lumped heat capacity analysis. Lumped heat capacity analysis. We will understand Biot number. We will understand Biot number. Okay. We will understand time constant. These concept. Fourier number, Hassler chart. All these things we will cover in the next class. Okay. So let's say Friday we'll meet for this, and then we will move on to heat exchangers. So we will cover heat exchangers in 2 classes. Okay. Chalo. Uske baad radiation 2 classes, and then convection 2 classes. This is what is our schedule for next classes. Okay. And then we will close our subject heat transfer. Okay. I hope it is clear. Okay. Chalo. So if you want to give it a read of these topics. Otherwise, whatever we have done, please keep revising. Even if you have revised it once, revise it twice, revise it third time. At least 3 revision is required for every topic. Okay. Chalo. So I will see you next on, I don't know, I'll share the schedule, and I think you will also get the schedule, but I am assuming it will be Friday, Saturday, Sunday anyway. So we will meet the same day. Okay. Chaliye. Thank you so much, Sahil. Thank you. I'll see you soon next time. Okay. Chalo.